Hi everyone, welcome to my A-level biology lecture series. In this lesson, we will explore the principle of respirometer. At the end of this lesson, you will be able to describe and carry out investigation using simple respirometer to determine the RQ of germinating seeds or small invertebrates, for example, blowfly larvae. Let's get started. So what is a respirometer? So respirometer is an equipment that we can use to measure the oxygen uptake during respiration. The following diagram shows a setup of a conventional respirometer. So in this respirometer setup, you can see that we have this experimental tube and a control tube. In both tube consists of this soda lime or KOH or NaOH solution. So this sodium hydroxide, potassium hydroxide solution or soda lime, they act as carbon dioxide absorbent. So why we need to include the soda lime or this carbon dioxide absorbent, I will explain it later. So in this setup, you can see that both chamber are connected to a capillary U-tube, which contain manometer fluids. You can use oil or the stain oil, okay, to act as the manometer fluid. So in this case, when we start the experiment, we just need to make sure that the level, okay, of the manometer fluid remains the same before we start the experiment. And this line is known as the origin. So how we can calculate the rate of respiration by using a respirometer. So the principle here, we know that any organism inside this respirometer, when they carry out respiration, they take in O2 and release CO2. However, this CO2 produced in the respiration is absorbed by carbon dioxide absorbent, for example, soda lime, or concentrated solution of KOH, as well as NaOH. So therefore, the volume inside this respirometer decreases over time. Why? Because O2 is consumed and CO2 is released, but this CO2 is absorbed by soda lime, for example. So therefore, any decrease in the volume of the air surrounding the organism results from the oxygen consumption. So we can actually measure the distance moved by the manometer fluids due to the oxygen consumption, and this distance is denoted by X millimeter. And we can actually measure it by reading the manometer fluid level against a calibrated scale. So, for example, in this case, after T units of time, you can see that there is an increase in the level of the manometer fluids. So you can see that this blue dotted line indicates the origin when the time equal to 0. After T units of time, there is an increase, okay, or this manometer fluids move towards the experimental tube. So we can actually measure the distance. Okay, so this distance is denoted by X millimeter. So how we can calculate the rate of respiration based on this distance? So we have to define the rate of respiration first. In this case, we define our rate of respiration as the volume of oxygen consumed per unit time. So it can be calculated using the following formula. So the rate of respiration equal to pi d over 2 square multiplied with the distance traveled by the manometer fluids due to the oxygen consumption divided by the duration of time. So where this d is a diameter of the lumen of the capillary U-tube, we can measure it in millimeter. And then X is a distance moved by the manometer fluid due to oxygen consumption after T unit of time. And T is the time taken for the process or for respiration to take place. Let us look at how we can use a respirometer to determine the RQ value. So first of all, as we have done previously, we determine the oxygen consumption, rate at a specific temperature. In this case, you can see that the X cm cubed of O2 consumption per minute, for example. However, in order to use this respirometer to determine how much or the volume of CO2 released during respiration, we need to modify this respirometer. Why? Because if this respirometer contains soda lime, it is impossible for us to measure the volume of CO2 released per unit time, because whatever CO2 released will be absorbed by the soda lime. So therefore, we need to repeat the experiment using the same organism at the same temperature, but without the soda lime or CO2 absorbed. So in this experiment, you can see that in this diagram, you will be able to see that we have removed the soda lime and then return the level of manometer fluid to the original position. So the manometer fluid reading will indicate whether the volume of O2 consumed equal the volume of CO2 produced, and this will suggest that RQ value equal to 1. Or the volume of O2 consumed is greater than the volume of CO2 produced, resulting in an RQ value less than 1. Or the third possible outcome, the volume of O2 consumed is less than the volume of CO2 produced, leading to an RQ value greater than 1. So this measurement allowed for the calculations of RQ value. However, in order to make our calculated RQ value become valid, there are some assumptions. So what are the assumptions in respirometer calculations of RQ? When using respirometer to calculate the RQ value, the following assumptions are made. First, steady metabolic rate. So it is assumed that the rate of O2 consumption remain consistent throughout the measurement period. So basically, when we have the first set of experiment with soda lime, we have this set of organism, right? Small invertebrate, for example, or germinating seed. We have to use back the same organism because our assumption here, the rate of O2 consumption remain consistent throughout the measurement period. So by using back the same organism, it more likely the organism have the same rate of O2 consumption, okay, or consistent O2 consumption. Number two, there's no variation in the activity. So it also assumes that the organism is not undergoing activity, example, movement or stress that would cause the sudden increase or decrease in O2 uptake. So by having this assumption, now let us look at what are the possible outcome after T units of time or duration of time with this respirometer without soda lime. So the first possible outcome. So in this outcome, after T units of time, we can see that there is no change in the positions of the manometer fluid. So it still remains at this level, the origin level. So with the assumption saying that, okay, with the same organism, as long as this organism is not is still alive, therefore respiration take place. So if we measure the distance moved by manometer fluid, it is zero distance, right? 0 mm, because there's no change. The manometer fluid still remain at the same level. However, if we want to know what is the distance moved by the manometer fluid due to the CO2 release, then we have to go back to our assumption. What is assumption? O2 consumption remain constant. So basically, these organisms, these small invertebrates, take in the same volumes of O2, and at the same time, they release the same volume of CO2. So let us look at this. So first, you can see that, okay, this is the amount of O2 consumption, okay, the volume of O2 consumption. So still remain constant. So the distance is X millimeter. And at the same time, they produce the same volume of CO2. So the distance moved by the manometer fluid here due to the CO2 release actually equal to X. So what is the distance moved by the manometer fluid due to CO2 release? The answer is X. And what is the RQ value? Because the volume of O2 consumption equal to X millimeter, the volume of CO2 release, okay, the distance moved by the manometer fluid due to CO2 release equal to X. So X millimeter, the RQ value equal to 1 because RQ value equal to X over X. So which is equal to 1.0. So the value 1.0 indicates that this organism carry out aerobic respiration, and the respiratory substrate is carbohydrate. Let us look at the second possible outcome. So in this case, we can see that the manometer fluid now move towards the experimental tube, okay, with a distance of Y millimeter. Can you see that? Y millimeter, okay, towards the experimental tube. Now, but what is the distance moved by the manometer fluid due to the CO2 release? If you look at this apparatus, we need to do some simple calculation. Go back to our assumption saying that these organisms carry out the same rate of O2 consumption. So basically, during this duration, against manometer fluid actually move X millimeter due to the O2 consumption, and Y, the level drop from this level to Y. Here, this is due to the CO2 release. So therefore, CO2 release can be calculated by subtracting Y from X. So therefore, the distance moved by manometer fluid due to CO2 release equal to X minus Y. So now, how we calculate RQ value? RQ value is equal to the distance moved by manometer fluid due to the CO2 release over the distance moved by the manometer fluid due to O2 consumption. So in this case, X minus Y, definitely the value is lower than X. So therefore, RQ value will be less than 1.0. So the calculation here, you can see that RQ equal to X minus Y over X. And because the value of X minus Y is lower compared to X, RQ value is less than 1.0. So it can be lipid, it can be protein used as the respiratory substrate. But we do know that when the RQ value less than 1 or equal to 1, it indicates that this is an aerobic respiration. Let us look at the third possible outcome. In the third possible outcome, you can see that the manometer fluid now move away from the experimental tube with a distance of Z millimeter. But is this due to the CO2 release? No, because we have to go back to our assumption saying that constant rate of oxygen consumption. So therefore, at first, the organism carry out respiration, take in this volume of O2, and then they release CO2. So from this level X to Z in this case, so this part actually filled with CO2, correct or not? Okay, so what is the distance moved by the manometer fluid due to the CO2 release? The answer is X plus Z. So try imagine O2 consumption, CO2 release. So therefore, X plus Z, okay, indicates the distance moved by the manometer fluids due to CO2 release. And the value of X plus Z definitely higher than X, so the RQ value greater than 1. So the calculation here show that RQ equal to X plus Z divided by X. So because X plus Z is higher value compared to X, therefore RQ value is greater than 1, which indicates that the organism actually carry out anaerobic respiration. So this is the principle that we need to know, okay, because I will have another practical series where we are going to focus on the respirometer itself. Yeah. With that, we have come to the end of this lesson. I hope you have found this lesson helpful. If you have any questions, again, feel free to leave them in the comment section. See you in the next lesson. Have a great day.